we're going to go over some, most asked tough coding questions in technical interviews. So we're going to go through several. So make sure you have your pen or pencil as well as paper down, because the way I learned software engineering and how to really tackle technical questions is through writing and absorbing through writing down the questions and answers instead of just watching an online lecture or just writing down in a Word notepad. So make sure you write this down on a pen and paper, because that's the best way to learn, at least for me. Okay, so let's start off with the first question. So the first question is going to be, given a head. So this is going to be a node question. So given a head, which is linked list's head, you have to determine if the linked list has a cycle within that. So we know that there's a cycle in a linked list if there's some node in that list which can be reached by continuously following the next pointer. And internal structure is that the position is used to denote the index of that node that tail's next pointer is connected to. Again, the position is leveraged to denote the index of the node that tail's next pointer is connected to.
We can see your only doc. We can't see this question actually.
Pardon?
We cannot see the question. We can just see the doc of HiCounselor.
So yeah, I'm gonna type the question down.
Okay.
Yeah. So the position is not passed as a parameter. So you have to return true or false depending on their cycle in the linked list. So I'm gonna write the questions down. So terminology. Okay, so let's give you an example. Let's say you have single node. Let's say the node just contains 1, right? Then the input's going to be head is equal to 1, because you're essentially having 1 element, and the position. Let's say the position is. Let's say the position is -1. So the output is going to be false, because there is no cycle in the linked list. Now, let's say you have a head of 1 and 2 and a position of 0. So that's going to return true, because we know that there is a cycle in the linked list where the tail connects to the 0th node. So again, you have head of 1, 2, then there is a cycle. Yeah, so if the head is 1, 2, and the position is 0, we know that the output is true because there is a cycle in the linked list where the tail connects to the 0th node. Another example is this. Let's say you have something like this, where the head is equal to 3, 2, 0, -4. And let's say the position is 1 here. Then the output is going to be true because there is a cycle in the linked list where the tail connects to the first node, which is, by the way, is 0th indexed. So it's going to be 0, 1, 2, 3. And then there is a cycle in the linked list where the tail connects to the first node. So you're essentially using the property of next, the head, to find whether there's a cycle in the list. And obviously you're not going to give in, this kind of diagram, but you're essentially given the input of head, and you're also given, yeah, that's it. So you're just given an input of head, and you want to find if there's a cycle. All right, so I'll give you a minute or two to solve it. Okay, so there's several ways to solve this. One is using something called a run and walk. And the second method is just using head and the next node continuously until you find if there's a cycle. So the first way is actually much more space efficient. So the algorithm is that, number one, you're going to use 2 pointers. Yeah. So here what we did is we used 2 pointers, one called head, one called run, and one called walk. And while the runs next node and runs next node, because remember it's running two per step. As long as those actually exist, then we run 3 things. Number 1, we set the walk to be the next node after it, and run to be 2 steps after it. So whenever the run is equal to the walk positioning within that while loop, we're going to return true because there's a cycle detected. Okay. So let's try another question. So the question is here. Let's say you have n number of boxes. Now, you are provided string called boxes, which is binary, and that has a length of n as well. So the boxes at I is going to be 0 if the ith box is empty. Boxes I is going to be 1 if it contains 1 ball. So in one operation, you can transition 1 ball from a box to an adjacent box, so the next to it. And box I is adjacent to box J if the absolute value of I minus J is equal to 1. So you have to note that after doing that, there may be more than one ball in some boxes. So you have to find and return an array of size n, where the array at the ith index is the minimum number of operations needed to move all the balls to the ith box. Again, so you have to find an array result of size n, where result at I is equal to min number of operations needed to move all the balls to the ith box. Every result at I is determined accounting for the initial state of the boxes. In one operation, you can transition a single ball from a box to an adjacent box. All right, so let's give you an example. Let's say your input is equal to boxes 0, 0, 1, 0, 0, 1. Sorry, 0, 0, 1, 0, 1, 1. the output is going to be 11, 8, 5, 4, 3, 4. Let's do another example. Let's say your input is equal to boxes at 1, 1, 0. The output is going to be 1, 1, 3, and the explanation is going to be as follows. So the first box, we know that you will have to move one ball from the second box to the first box in one operation, right? In the second box, you have to move one ball from the first box to the second box in one operation. Third box, you have to move one ball from the first box to the third box in 2 operations, and you move one ball from the second box to the third box in 1 operation. So again, the question is, given n boxes, and you're given a binary string boxes of length n, and the boxes at I is 0 if the ith box is empty, or 1 if it contains one ball. So in one operation, you can move one ball from a box to an adjacent box, and after doing that, there may be more than one ball in some boxes. So we have to return an array result of size n, where result at I is the minimum number of operations that's required to move all the balls into the ith box. Okay, I'll give you 1 or 2 minutes. Okay. So there are several ways to solve this again. And essentially, one of the most efficient ways is to use something called left sum and right sum. Essentially, you declare array of integers called left, right, and the result. So it's gonna be something like this. So let's start from the end. So we go from all the way 0 to the end, which is the length of the box, and we say that the result should be the addition between the left and the right of every ith element, right? So 0, it's going to be the combination of a left at 0 and right at 0, and at 3, it's going to be left at 3 plus right at 3. So we're just summing up individual left and right at the ith index. So we declared a couple additional arrays, left and right. So left is going to go from the left all the way to the right, and the right is going to go from the end to the beginning. If you look at the left, we're saying that the current left positioning is the summation between the previous left value plus the count. And the count is updated to be the addition of itself plus the character at the current position. So that's going to give you the index. And then the right is we're going to go from all the way to the right to the left. Again, the count is set to be the last character. And then the right is updated to be the current ith element. And so that is updated to be the 1 plus that. So the element to the right of that plus the count. So essentially, we're going from all the way to the right of the window, getting the element to the right, adding the count 1 by 1. So the count is updated to be the box's character at the current index. So count is also updated every iteration. There's a way to solve this by getting rid of the temporary arrays. Obviously, the problem asks us to return a new result array, and we won't consider that space in complexity analysis. So the space complexity is going to be constant. But that's a question that you can do it by yourself. But there's a way to solve this without the temporary arrays. But the solution is quite straightforward. We do a left sum and the right summation, and then we add it up to find the minimum operations that's needed to move all the balls into the ith box. All right. So the next question is also a very commonly asked question, which I faced interviewing for companies like Amazon or Google. And this is a tree question, BST, binary search tree. The question is, you're provided with BST, which is binary search tree. You have, please convert it to a greater tree so that every key of the original BST is changed to the original key plus the sum of all keys that's greater than the original key in BST. So what is BST? Number one, the left subtree contains only nodes with keys less than the node key. The right subtree contains only nodes with keys larger than the node key. But the right and left subtrees must also be BSTs. Okay, let's do an example. So let's say you're given this, right? Where the root is 4, 1, 6, 0, 2, 5, 7, null, 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 3, null, 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 because that's how you're given a input of root in a parameterized parameterized value. So the output is going to be 30, 36, 21, 36, 35, 26, 15, 33, and 8. Because remember, the goal is to convert it to another tree such that every key of the original BST is mutated to the original key plus the sum of all keys that's greater than the original key in BST. So for example, if you look at node 8 with the key 8, the greater tree is still 8 because there's no other tree such that the other node keys are greater than the original key. But if you look at 7, the value is updated to be 15 because 7 plus 8 is equal to 15, and 8 is greater than 7. So I'll give you guys 1 or 2 minutes. Okay, so to give you another example, if the root is, let's say, 0, null 1, obviously that was going to be, output is going to be null 1, null 1. Because you have 0, you have null, you have just 1, and the output is going to be 1 and 1. If you have something like, 1, 0, 2, 1, 0, 2, then it's going to be 3, 3, and then 2. So 3, 3, 2. Okay, so what are some of the ways that we can approach this? there's a couple of ways again. And the first way is actually to use iterative code. And the second one is use a recursive code. And then another way is to do reverse in order traversal. Now, what does that mean? The first way is the iteration. You use a stack to pop out the nodes in the reversed in order sequence. So at the beginning, you use a current pointer to point to the root, and you push into the stack the rightmost path of the current subtree. And then you pop out a node, you update the sum and the node value, and you point the current to the node's left child if there is any. And then you're going to repeat that step until the stack is empty and current has no left child. So let me write this down. So what do we do here? The way we approach this is we set a stack using a DQ or ADQ, and then we set the current to be the root, which is a node, and then we set the summation, a variable. So while the current node has something, and the stack is not empty, meaning also stack has something, we're going to do two things. Number one, we're going to run another while loop that runs as long as the current actually points to something. So, and then we save the rightmost path of the current subtree. Again, so we save the rightmost path of the current subtree. And then after that, we pop out by reversed in order. So that's what the current is equal to stack.pop does. We pop out by reverse in order. Summation is set to be summation plus the current value, which updates the sum. And then we update the node value, and then we move to the left branch. And then we return the root. So there's actually a recursive solution to this. So recursion is we actually leverage some tree node instead of instance variable. So the sum updates its value by reversed in order traversal of the nodes. So here you can see that in the reverse method, which is private helper method, we say that if the node is equal to null, we just return. And then we start from the right node, then we update the sum, then we update the node, then we go to the left node. So using a sum tree node instead of an instance variable. Obviously, the summation updates its values by reversed in order traversal of the nodes. So this is the recursive version, which is a little bit more compact with respect to the iterative version. So in the recursion method, we know that the time complexity is going to be O of n, because it's just linear, and then the space is going to be O of n because we're using a recursion stack. Now, if you go back to the iterative version, the time and space complexity is also equal to O of n. So in that version, we pushed into the stack the rightmost path, the current subtree. We deleted the node, update the sum and the node value, and we point the current to the node's left child if there is any. And we repeated this process until the stack is empty and the current had no left child. Okay, so yeah, this is the recursive version. Write this down because recursion always comes handy when you're doing complex binary tree questions or binary search tree questions. It's been always helpful. So yeah, I encourage you to find some binary tree questions. Maybe a question that I can really recommend is, finding the maximum binary tree. That is a very typical question that you get questioned, which is, you're given an integer array nums with no duplicates, and you have to find a maximum binary tree, which can be built recursively from the nums using an algorithm as follows. You create a root node whose value is maximum value in nums, and you recursively build a left subtree on the subarray prefix to the left of the maximum value. And then you recursively build a right subtree on the subarray suffix to the right of the maximum value. So, try this question out, maximum binary tree, because BSD is always questioned in technical interviews in FAANG companies. So I just want to say thank you for another great session. Again, if you need any assistance with job search in Silicon Valley companies or any tech world, I've helped my students land jobs in Amazon, Google, Stripe, companies like Square and Facebook. And HiCounselor is going to be an amazing resource for you. Again, you don't have to pay anything until you find a job. So there's going to be zero upfront payment. So the next cohort at HiCounselor starts very soon. So if you're interested, please apply on HiCounselor.com, and feel free to use my code Andrew, which is ANDREW, and you're going to get a 500 discount when you start paying HiCounselor after landing the job. So yeah, I want to say thank you, and I'll see you in the next session.